All right, so welcome to the seventh webinar in our series for GCSE science students. This one's going to be for GCSE Physics on the topic of the particle model of matter. Now, this topic has quite a lot of elements to it which cross over with the first topic that we covered for GCSE Physics, which was or rather the second topic, which was the topic on energy. We mentioned some of the ideas that we're going to be covering today in that webinar as well, but since that webinar I've received a lot of questions concerning heat and temperature, and again these are quite tricky concepts, partly because they are inherently quite tricky, but also partly because at GCSE level the ideas are not sufficiently well explained for you to really feel as though you've wrapped your head around them, and there's a reason for this. It's because those ideas are highly mathematical, and you know, they are very, very abstract, and so you really only get to grips with them properly later on in your education in physics, perhaps at degree level. But we're going to be attempting to lay to rest some of those outstanding questions. So let's start by taking a look at the basics here. Now, you should have come across the basic ideas of the arrangements and the movements of particles in solids, liquids, and gases already during your earlier years of teaching in science. But let's quickly review them because they are relevant to today's topic. So I'm going to use once again one of these PHET physics simulations. There are actually two versions of this simulation, a basic version and a more advanced version, which includes a model of molecular and atomic interactions, or rather just atomic interactions, the bonding between atoms. Now, if you're a GCSE student, obviously feel free to have a play with this and ask me any questions about this that you may have on the live chat on the private resources page. I'll be happy to answer them for you. But these models are very, very useful because they are molecular dynamics models. They are actual physical models of the way that these particles behave, taking into account the ways in which their atoms attract each other. And so let's start with some basics here. So in the solid state, we have the particles of a substance. Now, the substance that we're looking at here is neon. We could just as easily look at other substances here, like argon, which is another group 0 element. These are monatomic elements, and so these circles represent individual atoms. But we can also look at molecular substances like oxygen, which is made up of pairs of oxygen atoms bonded together into molecules, or we can even look at water molecules. So let's keep it simple, though. Let's just take a simple monatomic substance like neon. So in the solid state, the atoms are arranged in orderly geometric arrangements. They vibrate around these averaged fixed positions in this crystalline lattice structure, and they don't have very much kinetic energy, and the forces between these particles are sufficient to hold them in those average positions for the most part. Now, when we go to the liquid state, we see that the particles are disordered. They are moving randomly, and some of them have sufficient kinetic energy to break free of the surface of the liquid, as you're seeing here, and go off into the gas state. So this is evaporation that you're seeing here, and as you can see, the water will take the shape of its container, whereas the solid maintains its own shape. Now, if we compare that with particles in a gas, the particles in a gas are moving more rapidly on average and at the same temperature, and the forces between them have been overcome to the extent that they can move essentially freely between each other and collide often with each other and with the walls of their container. Now, we're going to be coming back specifically to the gas state because we need to also understand in this topic the idea of gas pressure. But very briefly here, the reason why gases exert a pressure on the walls of their container is because they collide frequently with the walls of their container, and each individual little collision between those particles and the walls of their container exerts a small force for a very short period of time. And the sum of all of those millions of collisions per second is what exerts that pressure over that area of the inside surface of the container. Now, if we were to heat this solid, once it reaches a particular temperature, the particles have sufficient kinetic energy to move past each other and move into the liquid state. And eventually they will also turn into a gas. Now, we're going to be looking at changes of state a bit later on. If you really want to explore changes of state using this model, in the basic version, you can simply go to phase changes, and you have a rather more elaborate setup here where you can add particles to the sample of matter in the chamber, you can change the pressure. Now at this point, there's 0 atmospheres of pressure because the particles are not colliding with the walls of the container, but we could just as easily turn this substance into a gas, for example, and at that point you would see that there is a pressure being exerted on the walls of the container because of the collisions between those particles. So once again, we're going to be exploring changes of state a little bit later on in this webinar as well. So let's have a look now at summarizing what we've just been talking about in terms of explaining the properties of solids, liquids and gases in terms of the arrangements, the forces between and the motions of those particles. So firstly, in the gas state, the particles are widely spaced apart and are in a constant state of motion. The frequency of collisions is rather high because of the motion of the particles, and they collide frequently with each other and with the walls of their container. Now, the kinetic theory of matter is the proper term used to describe the aspects of physics which have to do with explaining the observable, measurable properties of matter, like density and hardness and things like that, in terms of the arrangements, the motions, and the forces between the particles in those substances. So, in gases, we have a large amount of space between the particles. The particles are moving rapidly, and the forces between those particles are comparatively weak. And the particles, because they're moving randomly, will spread out to fill their container, and also diffusion happens relatively quickly in gases. Now, if we contrast that with a liquid, in the liquid state, the particles are about as closely packed as they are in a solid on average, but they are randomly moving. They are randomly ordered and they're randomly moving. And also, unlike in a solid where they're moving vibrationally, in a liquid and also in a gas, the particles are moving, as we saw in that simulation, in straight lines until they collide with each other and then change direction. So the particles are moving past each other in a liquid and in a gas, whereas in a solid, they're moving vibrationally. So once again, diffusion does occur in a liquid, but it happens rather more slowly. In a solid, the particles are moving in a vibrational manner around these average fixed positions in this regular geometric arrangement that we call a lattice structure or a crystal structure. And they are tightly packed together, very, very close to each other, and the forces between them are comparatively stronger than they are in a liquid or in a gas. So diffusion in solids does not occur. Now, in most physics specifications, you're not required to understand or to be able to explain diffusion, but if you're studying GCSE Physics as a separate science subject, you're going to be studying most likely chemistry as well, and also biology. And again, diffusion is the random movement of particles from a region where they're in high concentration to a region where they're in low concentration. Now, since the particles in a solid are unable to move translationally the way that they do in a liquid or a gas, diffusion doesn't occur in solids. So we have gases having low density and rising typically above liquids. So if you have gas released within a liquid, then typically the density of the bubbles of gas is lower than the surrounding density of the liquid, and so gases will rise in a liquid. In a liquid, these are medium in density and will usually, not always, but will usually rise above objects made of the same substance but in the solid state. Now, in a solid, solids typically have a high density and usually, not always, but usually will sink below the liquid made of the same molecules but in the liquid state. But there is one common solid that floats on its own liquid. So I'm going to pause here and let you guys answer this question. Which common solid will float above its own liquid? Very good. Yes. So most of you got the correct answer. Well done. Yes, water. Water, even though it is comparatively common as far as human beings are concerned, I mean, 3/4 of the Earth's surface is covered with the stuff. Your body is mostly made of water by mass. But nonetheless, it is a very unusual material. One of the unusual properties of water is that the solid in the solid state, it has a lower density than in its liquid state, and this causes solid water or ice to float on liquid water. Part of the reason for this is because of the structure and the bonding in solid ice. Now, to go back to the simulation briefly to show you why that's the case. So if we choose, let me reset this. So if we choose water, you see that unlike these monatomic or even molecular solids, where the particles are very, very closely packed together, in water, the water molecules are polar. The small white circles here on this water molecule here represents the hydrogen atoms which are bonded to the oxygen atom here, the red one. Now the hydrogen atoms are slightly positively charged with respect to the oxygen, which in contrast is slightly negatively charged with respect to the hydrogens. The water molecule is neutral overall, but it has this internal polarity where the oxygen end is slightly negative with respect to the hydrogen ends, and the hydrogen ends are slightly positive with respect to the oxygen end. So the water molecules will arrange themselves like this, where the hydrogen atom on one of the water molecules, the one that I'm highlighting here, is attracted to the oxygen atom on another neighboring water molecule, like this one or this one. And so the water molecules in the solid state arrange themselves in this manner, which is actually a tetrahedral arrangement. And because of this, they're actually more widely spaced apart on average than they are in the liquid state, as you can see here. And so here we can see that water, liquid water, is actually more densely packed in terms of its particles than solid water. And therefore, if you have a piece of solid water sitting in liquid water, because it is less dense, it experiences less gravitational attraction downwards, and therefore will float on the water. So this is the reason, in a nutshell, in a simplified way, why solid water will float on liquid water. Liquid water has a higher density than solid water. All right, so I'm mentioning density quite a lot here. So density is one of those properties that you need to be able to explain in terms of the arrangements, the motions, and the bonding between particles. So let's have a look at the concept of density now. Now, density, generally speaking, is actually very easy to calculate. The formula for density, which most of you are probably familiar with, is for mass density. So density of an object is equal to the mass of the object divided by the volume of the object. Now, the symbol for density is the Greek symbol rho, which looks like a little P with a kind of forward pointing tail. And we have this is equal to mass by volume. Now, since the standard units of mass are kilograms and the standard units of volume are cubic meters, the standard units of density are going to be in kilograms per cubic meter. So kilograms per meter cubed is the standard unit of mass. Now, if you have more mass in the same volume, then you're going to have a higher density. So again, going back to our example of liquid water, let me just bring up that simulation again. So if we look at liquid water and imagine that we have the same volume of liquid water. So if we imagine, let's say, a cube or a cubic container which is filled with liquid water, then the particles in liquid water are much closer together in that one cubic meter. Let's just imagine that our container has a volume of a cubic meter. The particles in liquid water are closer together. Now, mass or matter is made up of particles, whether they're atoms or molecules or ions or whatever. So if we have a container, let's imagine we have a container of 1 cubic meter here. Bad drawing skills still on the graphics tablet. Eventually I'll learn how to use one of these things properly, but you get the point. So let's imagine that our container has sides of 1 meter in length, just to make life very easy for us. So what we have here is a cube of volume 1 times 1 times 1 meter. So the volume here is 1 meter cubed. So if we imagine that we have liquid water molecules which take up the entire space of this container, then we're going to have a certain amount of matter, a certain amount of mass in this volume of space. But if we imagine then that instead that the particles in the container are then changed to liquids to water in the solid state, those particles are more widely spaced apart, which means you're going to be able to fit fewer particles or less mass into this same volume of space. Now, if you've got the same volume in both cases of liquid water and solid water, but in solid water you have less mass stored in that volume, then you're going to have a lower density. So this is the reason that the solid water, this is kind of the mathematical reasoning whereby we can say that solid water has less mass per unit of volume, or less density, than liquid water. So this is the equation for density. Now, in the similar way, generally speaking, going back to that simulation once again, generally speaking, if we look at general substances here, not water, water is a bit of an exception here, but generally speaking, neon, if we have neon in the solid state, then the particles are very close together. In the liquid state, they're somewhat further apart on average. In the gas state, they're very widely spaced apart. And so if we have a fixed mass or rather a fixed volume of a container, we're going to be able to fit fewer gas particles per unit of volume in that than liquid particles. And similarly, you're going to have a slightly more solid particles in that same volume of space than liquid particles. So a gas has the lowest density of the three states of matter. Solids typically, not always, but typically will have the highest density because you have more mass or more particles per unit of volume, and the liquid is somewhere in between. Now again, water is a bit of an exception to this rule, but there's always an exception. All right, so these are the states of matter. Now, another thing that we need to discuss is changes of state. Now, heating or cooling can, when you hit a particular temperature, cause a change of state from solid to liquid to gas, or from gas to liquid to solid if you're cooling. So the change of state that describes the when a solid turns into a liquid is, of course, melting. Then from a liquid to gas, we have evaporation or boiling. Now, evaporation is a passive process that does not require heating. Evaporation for a liquid will happen at any temperature, theoretically speaking. So again, going back to a liquid here, you'll see that most of the particles of the liquid at a particular temperature are arranged very close to each other. But again, some particles will have slightly more energy than others, and so will be some of them, if they come near the surface of the liquid and they have sufficient kinetic energy, they can break free of the surface of the liquid and go into the gas state. So this is evaporation happening here. Now, evaporation does not require external heating. It just happens at any given temperature. It happens at a higher rate at higher temperatures and a lower rate at lower temperatures. But it does happen at any temperature. However, boiling is a change of physical state which does require heating to a particular temperature called the boiling point. Now, going in the opposite direction, we have cooling. So if we cool the gas down, we eventually hit a temperature at which it will turn into a liquid. This is called condensation. The temperature is called the condensation point. And then we have the liquid turning into the solid at the freezing point. So we're going to look at changes of state a little bit later on. So that takes care of a kind of introduction to this topic here. This has really just been a review of what you should have already learned and recalled from earlier years of your science teaching. So we'll get into changes of state in a little while. We'll come back to that. Okay. So one of the one topic, or the one idea, the one set of concepts in this topic that most of the students voted for in the private resources page was the distinction between these terms: heat, temperature, internal energy, and thermal energy. This seems to cause a lot of students a lot of confusion. So we're going to start with that after our little introduction and review of the fundamentals. I see that there's a lot of questions coming through in the chat box. Please, guys, do type those into the Q&A section. At least that way, I'll be able to sort through them more clearly, and other students will be able to upvote them. So if you do have any questions, please do type those into the Q&A box. All right, so let's start with the concept of temperature, or rather, let's start with the concept of heat. So heat is generally defined as the transfer of internal energy from one object at a higher temperature to another object at a lower temperature. So the term heat requires us to understand what we mean by temperature, because it is defined usually in terms of temperature. At least it is the way that the definition for the term heat appears in GCSE specifications is it's defined in this way. Heat is the transfer of internal energy from a higher temperature object to a lower temperature object. Now, the scientific unit of heat is named after James Joule, and so it's called the joule. Now, heat is, in order to understand heat, we first need to understand the term temperature, and we also need to understand this term here, internal energy, which again is a kind of a difficult term for people to wrap their heads around. So let's quickly look at how these terms are defined generally speaking, and then we will go on to have a look at what these definitions actually mean. So let's see here. So we've got heat. Heat is usually described as the transfer of internal energy from a hotter or higher temperature object to a lower temperature object. So it's a transfer of energy. So we're talking about, we've used the terms temperature and internal energy as well as heat, so these also need a definition. So now temperature is perhaps the most difficult one to define. Temperature is usually described as the degree of hotness or degree of coldness of an object. Now, as we'll see, temperature is in fact better defined. It's a way of measuring, so it's a measure of the average kinetic energies, average kinetic energies or average kinetic energy, because average is one thing, average kinetic energy of the particles of an object. So temperature is a measurement of the average kinetic energies of the particles, the microscopic particles that make up any particular object. And so it's an average because at any given temperature, some particles will be moving slightly more quickly, some particles will be moving slightly slower, but the average kinetic energies of the particles of any object at is a description of, or rather temperature is a description of that average. The higher the temperature, the faster the particles are moving on average. The lower the temperature, the slower the particles are moving on average. And once again, we can see that in our simulation. So if we have a solid, the particles are moving relatively slowly. You give them a bit more energy, they're moving a bit more quickly because they're moving to a higher temperature. So the higher the temperature, on average, the faster the particles tend to move. Now, what about internal energy then? Now, this is the one which causes a lot of issues, partly because there is another term which is a little bit more vague, which still gets thrown about a lot and tends to get confused with internal energy. So let's start by giving a rigorous definition of what internal energy of an object is. So internal energy. Internal energy of an object is described as the sum or the total of all the kinetic and potential energies of all the particles which make up an object. So it's when you add together all of the kinetic energies, all of the potential energies of all of the particles that make up an object, you have the object's internal energy. That's what internal energy means, and this is the way that it's defined, and this is actually a very good definition for internal energy. The issue is that a lot of the time we use the term heat in association with another term, thermal energy. Now, thermal energy is a bit more slippery and a bit less useful than the term internal energy. Depending on who you ask and where you look and which context that you're dealing with, you're going to find slightly different definitions of this, which kind of causes issues. So at GCSE level, or indeed at A level, or even at degree level, at undergraduate level in physics, it's okay to define internal energy as the energy stored in an object which is associated with the kinetic, or the motion rather, of the particles of the object, the motions of the particles which make up the object. So, thermal energy is just the kinetic energies of the particles which make up the object, whereas internal energy includes the thermal energy, includes the motions of the particles and the energy associated with them, but it also includes the potential energies of all of the particles. Now, the other problem here is that the slightly more astute students even will often ask the question, okay, if there's such a thing as internal energy, then surely there must be such a thing as external energy as well. Well, yes, that is the case. Internal energy of an object, remember, we're talking about a particular object. So imagine we have this pen, or in fact, let's use a slightly different example. Let's imagine we have a boulder sitting on top of a hill. So here is our boulder. So we have our boulder sitting on top of the hill, and at the bottom of this hill, so at the bottom of this hill, we have a wall. So let's imagine we have a wall at the bottom of this hill. Now, in our hypothetical situation, let's imagine that this wall is completely immobile. It doesn't matter how much force. This is the proverbial immovable object. It will not move, it will not vibrate, it will not budge at all. And let's also imagine that this is a closed system. And again, if you want understanding of that, then I would suggest going back to that first webinar that we did, or rather the second one on energy earlier this week. So let's imagine this is a closed system where we're just dealing with gravitational potential energy and also the kinetic energy, the mechanical kinetic energy of this boulder as it rolls down the hill. Now, at this point, before it starts moving, this system has gravitational potential energy. So the energy possessed by the boulder at this point is gravitational potential because it is at a certain height above ground. However, let's just imagine that the boulder then rolls down the hill. So it gets to this point where it's moving down the hill. And finally, it reaches the point where it crashes into the wall. But let's just imagine that it crashes into the wall and comes to a dead stop. Now, at the macroscopic level, so we're not talking. So if we're just looking at this situation, let's say we are standing somewhere over here and we're watching this boulder roll down the hill and come to a crashing halt as it hits the wall. Let's imagine that no energy is lost as heat or sound or friction on the way down, because again, this is a closed system. What this means is that at the moment it hits the wall, at that moment, at that instant, the system doesn't have gravitational potential. It has converted all of that gravitational potential into kinetic energy here. But then as soon as it hits the wall, if it comes to a stop, then where is the kinetic energy gone? Surely, it seems on the macroscopic scale at least, on the scale of, ordinary sized objects like this wall and the boulder, it seems like the kinetic energy that it had the instant before it hit the wall has suddenly disappeared. But it can't have, because energy is conserved. The energy must have gone somewhere. The key here is that so far, all we've been talking about is external energy. The boulder, as it moves, has this coordinated motion on the macroscopic scale, which is associated with external energy. The external energy of the boulder as it rolls down the hill is kinetic, and it remains kinetic until it hits the wall. When it hits the wall, that external kinetic energy has been transferred into the vibrational kinetic energies of the microscopic particles that make up the object. So external energy is the energy which is observable on a macroscopic scale. So it's a kind of arbitrary distinction. Again, energy is this kind of it's an abstraction. It's an abstract concept. It's given meaning by calculation and by kind of logic in physics. It's not something that's directly. It can't be easily perceived. It can't be easily measured directly. It's a mathematical abstraction. So we tend to make arbitrary classifications like internal and external energy because we can see boulders, but we can't see with our own eyes the microscopic particles that make up those boulders, but we can show by experiment that they do exist. So the particles inside the boulder as it's sitting on top of the hill are vibrating, they're moving at a certain rate. And when it hits the wall here, the kinetic energy gets transferred into the vibrational kinetic energies of the particles of the object, which then vibrate much more rapidly because the energy, the external energy, has been transferred into internal energy, the motions of the particles and also the potential energies of those particles, which are to do with the bonds between those particles. And so internal energy is the energy associated with an object, but which you can't observe from an external perspective. So right now, this pen, if I held it perfectly still, it has gravitational potential energy, but it also has internal energy because the particles that make up the pen are in a constant state of motion. They have individual kinetic energies, which when you add them all up and add also their potential energies, you have the total energy stored in the object. This is called the internal energy. So internal energy is the sum of all of the kinetic and potential energies of all of the particles which make up an object. External energy is the sum of the kinetic and the mechanical kinetic, the macroscopic kinetic energy. So if the pen was moving in this direction, it would have kinetic energy, mechanical kinetic energy, and it also has external gravitational potential energy as well, because on the macroscopic scale it's in a gravitational field and the gravitational field can accelerate it. So there is a distinction between internal and external energy, but because this topic is about particles, we're talking specifically about the energies associated with particles. So if we see here, temperature is a measure of the average kinetic energy of the particles, the microscopic bits of matter that make up an object. Internal energy is the sum of all kinetic and potential energies of the particles that make up an object. Thermal energy, again, a bit more of a kind of loose term. This specifically describes the motions of the particles that make up an object. So here in this topic, we're talking about internal energy. Now, temperature measures on average how fast those particles are moving. So what we can say here is the gravitational potential energy, the external gravitational potential energy, gets transferred into the kinetic energy store, the mechanical kinetic energy store of the boulder as it rolls down the hill, until eventually when it crashes into the wall, that kinetic energy gets transferred into the thermal energy. The boulder itself will increase its temperature because this kinetic energy has been transferred to the particles of the boulder, which then move more rapidly. So the external energy in this situation is eventually transferred into internal energy. So external energy is the type of energy stores which are observable and have observable change observably in macroscopic situations, or are associated with observable changes on the macroscopic scale. Internal energy concerns the microscopic scale, the particles that make up the objects, the energy stored in their motions and in their positions relative to each other, because again, particles have bonds between them, and whenever you have electrostatic attractions like bonds, you have energy stored in those systems. So that's what internal energy is, and that's the distinction between these terms. All right, so let's move on then. So heat is the transfer of internal energy from a higher temperature object to a lower temperature object. Now, the problem with temperature is that it can be defined either operationally by measurement, or it can be defined theoretically. Now, the theoretical definition of temperature has to do with the zeroth law of thermodynamics, which we're not going to get into here, but it's essentially defined as the quality of materials which determines the direction of heat transfer. So if heat is being transferred from object A to object B, according to the theoretical definition of temperature, object B is at a higher temperature, or object A is at a higher temperature than object B. The direction of heat transfer is determined by temperature, and therefore temperature is defined in terms of the direction of heat transfer between objects until they reach thermal equilibrium with each other. So temperature, in a very simple manner, again, this is simplifying things to the point of almost absurdity here. Temperature is a measure of the degree of hotness or coldness, but it is more accurate to describe temperature as a measure of the average kinetic energies of the particles of objects. Now, there are several different temperature scales because over the years, before there was a theoretical definition of temperature, people intuitively knew that there was something about hotness or coldness that was different. You touch a hot object, it feels very different from touching a cold object. And so various types of thermometers were used to measure the degree of hotness or the degree of coldness, and therefore various temperature scales evolved from the use of those thermometers. So we've got degrees Celsius, where on the Celsius scale, 0 degrees Celsius corresponds to the freezing point of water, and 100 degrees Celsius corresponds to the boiling point of water. Now, room temperature is about 25 degrees C, unless you happen to be in this room where it's about like a billion degrees C, because I'm sweating through my clothes here. So here we go. Measuring temperature then. So what good are thermometers? If they all give different readings for the same temperature? They are useful to some extent, as long as if you're discussing temperature between two scientists, both scientists are using the same temperature scale. If they're using different temperature scales, then you need to be able to convert between them. So thermometers use different variables, different physical properties of matter which change with temperature as a means of measuring temperature on these different scales. So you have various designs of thermometer, all of which will use different physical phenomena which change as the temperature changes. So for example, you have thermocouple thermometers like this one, which measure temperature electrically. In terms of the way electrical properties of materials will change with changing temperatures. You also have liquid in glass thermometers like this one, where you have a certain volume of liquid, and the volume of the liquid will change with temperature, and you can use that to gauge the temperature of that liquid. So, temperature on average, in a very for the average person, is a degree of how hot or cold something is. But at the molecular level, the temperature is a measurement of the motions of particles, the average kinetic energies of the particles. And if the temperature is increasing, what that tells us is that the average kinetic energies of those particles are also increasing. So the Celsius scale was determined and defined by Anders Celsius, this gentleman over here, where originally the boiling point of water on this scale originally was actually 0 degrees C, and the melting point was actually 100 degrees C. And so in a sense, Anders Celsius proposed the Celsius scale, or what became known as the Celsius scale, backwards in comparison to the way that we measure it today. Now, this was reversed by Carolus Linnaeus to give today's temperature scale, where the melting point of water is 0 degrees centigrade and the boiling point is 100 degrees centigrade. But like most other temperature scales, the Celsius scale is a bit unsatisfactory, because if we now know that the temperature measures the average kinetic energies of particles, then how can you have a negative average kinetic energy of particles? Negative temperatures are not particularly convenient, and also what makes the Celsius scale better than the Fahrenheit scale, for example? It isn't really better or worse, to be honest. It's just a scale by which we measure things. What we need is an absolute scale of temperature, a scale of temperature which actually corresponds with what we know as physicists to be what temperature actually refers to. So in other words, we need a scale that relates the numbers on that scale to not some thermometric variable like the expansion or contraction of a liquid in a glass tube or the electrical properties of a thermocouple thermometer. What we need is something which actually relates the numbers that we use to describe temperatures to the average motions of particles. So enter Lord Kelvin. So Lord William Kelvin, in 1848, he proposed an alternative temperature scale, which was independent of the properties of any particular substance, and it was based solely on the kinetic energy of particles. Now, Kelvin's scale set 0 as being minus 273 degrees centigrade. So absolute 0 is about minus 273 0.15 degrees centigrade. This corresponds on the Celsius scale to what is 0 Kelvin, the absolute 0 of temperature. Now it's called absolute 0 because there can be no colder temperature than this. By definition, if temperature is a measure of the average kinetic energies of particles, then how are we going to get then the 0 of the absolute scale of temperature must correspond to the temperature at which the particles stop moving altogether. So there can be no negative numbers on the Kelvin scale because the scale corresponds to the average kinetic energies of particles. So to convert Celsius temperature to Kelvin, you need to remember that 0 degrees centigrade is 273 Kelvin. So in order to convert 100 degrees centigrade to Kelvin, we subtract 270, or we add rather 273 to 100, and we get 373 Kelvin. So let's have a look at some common temperatures on the Celsius scale and how they compare to the temperatures on the Kelvin scale. So here we see that the boiling point of water, 100 degrees centigrade, corresponds to 373 Kelvin. So the hottest temperature on Earth feels like it's in this room today, but the hottest temperature ever recorded on Earth is about 56 degrees centigrade. And then we have the body temperature, which is about 37.5 degrees centigrade. Then we have the freezing point of water, which is 0 degrees centigrade on the Celsius scale. It's about 273 Kelvin. If we go to the where is it here? Should pop up. Here we are. The coldest temperature on Earth recorded was 184 Kelvin. So just shy of minus 90 degrees centigrade. So oxygen, the melting point of oxygen is 90.2 Kelvin. So this gives you the freezing point or melting point of oxygen. Now, if we go even colder than this, the surface temperature on Pluto is 53 Kelvin. If we go even colder than this, we eventually get to the temperature of free space. So the temperature of free space outside of the Earth's atmosphere and out into the solar system and intergalactic space is about 3 Kelvin. And finally, absolute 0 is the temperature at which all particle motion stops. So there can be no negative numbers on the Kelvin scale because the Kelvin scale corresponds to not these arbitrary methods of measuring temperature like the ones used in thermometers. It actually is connected to the theoretical definition of temperature. Thermometers allow us to define temperature operationally by measurement, but what Lord Kelvin did was he used the properties of gases and how they change at different temperatures to determine a scale which isn't based on physical properties, it's based on the theoretical definition that as the particles move faster, the temperature is higher. So on the Kelvin scale, as the temperature decreases, the particles move less rapidly on average until eventually when we hit 0 Kelvin, the theoretical lowest temperature, there is no particle motion at all. So the way that Kelvin did this, as I say, is to do with gas, the behavior of particles in a gas. Very simply, to kind of simplify things somewhat, the way that he did this was he took, on the Celsius scale, if we imagine we have this axis here, which corresponds to the temperature on the Celsius scale. Let me That should not be happening. Apologies, guys. There we go. All right, so not very good at drawing vertical lines, so I'm not going to trust that to my free hand. All right, so if we imagine that we measure the pressure of a gas. Now, the pressure of a gas, as we'll see in a second, has a lot to do with particle movement. Now, what Kelvin did was he measured the pressure of a gas at increasing temperature. And what he found was something like this. So he took measurements of the temperature of a gas at different, or the pressure of a gas at different temperatures. And what he did was he extrapolated the measurements of temperature backwards. So he drew a line of best fit, and where that line of best fit crossed the horizontal axis, now obviously on the Celsius scale, so this is in degrees Celsius, but he could take measurements at reasonable temperatures, even at 0 degrees C. But you can't reasonably take measurements at minus 273. But what he did was he took these measurements of the pressure of a gas, which he knew to be related to the motions of the particles of a gas, and he deduced that if you extrapolate these back, then the absolute lowest temperature possible would be the temperature at which the pressure of that gas was 0, because the particles were not moving at all. And so this temperature here on the Celsius scale, which he worked out was minus 273 degrees Celsius, this must correspond to the lowest possible temperature. In other words, he set this as 0 Kelvin for that reason, because he deduced that if the pressure of a gas is related to its temperature, because as the particles move faster, the gas molecules collide more frequently with the walls of their container, then if these are the measurements he took and he draws a line of best fit, then the 0 of pressure, where this line crosses the horizontal axis, where the pressure is 0, this must correspond to the lowest and coldest temperature that could exist. He measured this on his graph as minus 273 degrees centigrade, so he set his scale, the 0 of his scale, at this temperature, because this is the temperature at which the pressure of a gas must be 0 and its particles must have stopped moving. So there can be no colder temperature than this. And that's basically the way that the Kelvin scale was defined. So once a substance has boiled and become a gas, increasing the temperature will increase the average kinetic energies of the particles. And if the gas is enclosed in a sealed container, then the particles are going to be colliding with the walls of that container and exerting a pressure on the walls of that container. So at 40 degrees centigrade, 313 Kelvin, for example, at this temperature, there is a certain amount of pressure due to the collisions of the particles with the walls of the container. At a higher temperature, the gas pressure increases. At still higher temperatures, the gas pressure continues to increase. And so, so the gas is produced by the particles colliding with the walls of the gas pressure is produced by the collisions between the gas molecules and the walls of their container. As the temperature rises, the average kinetic energies of the particles rise, therefore they're moving more quickly. Therefore, the force with which they collide with the walls of the container and the frequency of those collisions increases, so the gas pressure increases. So the kinetic energy of the gas can be calculated using this. So one particle of this gas will have a kinetic energy of half times its mass times its velocity squared. So m is the mass, v is the speed of the particle, or the velocity of the particle. Now, the pressure of a gas can be calculated using an equation which you don't necessarily need to know, but it's this. It's related to 2/3 K times T, K being a constant. So T is the temperature in Kelvin, K is a constant, which again, don't need to go into details about this. This is a simplified kind of, for GCSE students, consumption understanding of some aspects of thermodynamics here. So as the Kelvin temperature scale relates temperature to the kinetic energies of the particles, and therefore pressure to the kinetic energies of the particles, as we saw in the previous couple of slides, these two equations can be combined to give something like this, which can then give us the reason why the average kinetic energies of the particles is directly related to the temperature in Kelvin. Because if temperature is T and this is just a constant. 2/3 times a constant is just a constant. Then to get T, we can divide this side by this constant. And in fact, that is what we do. And this shows us directly that temperature is a measure of the average kinetic energies of the particles. And so this is again why the Kelvin scale is called the absolute scale of temperature. It is not reliant on some physical property that changes with temperature in a thermometer. It's reliant upon the theoretical definition of temperature. So, as the temperature of a gas increases, so does the kinetic energies of the particles of a gas. And so if we heat a gas using a water bath in a sealed container and attach a pressure gauge to it, as the thermal energy is passed from the water to the gas inside the flask, the pressure will rise until eventually the release valve opens to prevent the round bottom flask from blowing up. Now, speaking of explosions, when gas pressure increases to a point where the container cannot withstand the pressure, then a seal will break or an explosion will occur. So heating sealed containers, which then explodes, is one of the most common causes of laboratory accidents. Now, rapid increases in gas pressure and subsequent explosions obviously have been exploited for centuries for military purposes. So this is a photograph of the controlled explosion of mines in Iraq. So let's take a quick look at gas laws before we break in 5 minutes' time for the first 5-minute break. So the pressure, the temperature, and the volume of a gas are some of the measurements that were made by the scientists who were most responsible for the early development of the kinetic theory of matter. It all really started with Robert Boyle. I mean, you could argue it started earlier than him, but Boyle and Charles and Gay-Lussac. These were all scientists that made measurements of the ways in which the pressure, the temperature, and the volumes of gases will change under different conditions, and this was the foundation of the kinetic theory. Now, the kinetic theory assumes that particles in a solid or in a liquid or in a gas, let's go back to the simulation here, the kinetic theory of matter, which in many GCSE specifications is referred to as the particle model of matter, the kinetic theory assumes that these are point masses. In other words, they occupy no physical dimensions. It also assumes that they collide elastically with each other and with the walls of their container. So, I mean, obviously these are not true of real gases. Real gas molecules do have mass, and they do, that mass does occupy a certain tiny amount of space, and the collisions are not elastic necessarily, because gas molecules, like water molecules for example, they do have chemical bonds between their atoms, and those chemical bonds vibrate kind of like springs. And so these are assumptions of kinetic theory which are not necessarily true of real gases per se, but they're true enough that we can use kinetic theory to accurately model the behavior of real gases. So the laws, the gas laws that we're going to be talking about, were based upon a theoretical modeling of a gas as being composed of particles with zero actual size, which collide perfectly elastically with each other. And this theoretical model of a gas is referred to as an ideal gas, in which the particles have no size and also no interaction takes place between them, and they collide elastically with each other. However, these laws still do describe very accurately the behavior of real gases. So Boyle's law, named after Robert Boyle, this relates pressure to volume. So Robert Boyle was an extremely important scientist, not just for Boyle's law, but for a number of other reasons. He was one of the first to apply what we describe in modern science as a quantitative approach to science. He did experiments after experiment after experiment, and he scrupulously and meticulously noted down every single measurement, documenting his procedures, his equipment, his materials, for every scientific investigation in minute detail. Now, this allowed his published work to be reviewed by other scientists, and this is what we now call peer review. And it also allowed, because he made such meticulous notes about his methods and his equipment and his procedures, this allowed his work to be independently replicated by other scientists who could then confirm that the work that he was doing was reproducible. And so all of this is now a key part of the way that science is done. And so Robert Boyle was really, in some ways, at least in terms of experimental science, he was by far superior to Isaac Newton, because he was far more of a rigorous experimentalist, and his approach to doing experiments is the basis of what we now call the scientific method in large part. So Robert Boyle related the pressure of a gas to its volume by an equation that looks like this. So P is the pressure of the system, V is the volume of the gas. And what he said was that at any fixed temperature, if you change the pressure, then the volume will change such that the product of the pressure and the volume, when you multiply the pressure times the volume, you always get a constant. So this was Boyle's law, that pressure times the volume of a gas at constant temperature will be a constant. So if you increase the pressure, the volume must decrease. If you increase the volume, the pressure must decrease. Again, this assumes that the gas is being held at a constant temperature. So Charles's law, sometimes called Gay-Lussac's law, and this goes to a bit of a controversy and in the kind of history of science. This was developed by another very important scientist, Jacques Charles, and he said that at a constant pressure, if you keep the pressure of a gas constant this time, and either change the volume or the temperature, the volume divided by the temperature is always constant. So if you increase the volume, you must also increase the temperature in order that the pressure remains the same. And if you decrease the temperature, you must also decrease the volume in order that the pressure remains the same. So this was Charles's law. And the third law, important law, was Joseph Gay-Lussac's law. And this related pressure to temperature, assuming this time that the volume was constant. So if you keep the volume of a gas constant, but you change its pressure, its temperature will change. If you keep the volume of the gas constant and you change the temperature, its pressure will change in such a way that the pressure divided by the temperature is always a constant. So these three laws, these key discoveries by these three scientists, were the basis of what we now call the kinetic theory of matter and modern thermodynamics. And these can also all be combined together in one overall law. So if we take the three laws that we've just looked at, Boyle's law, Charles's law, and Gay-Lussac's law, we can combine these into one equation, which is sometimes called the combined gas law. So this states that if you take a gas and you multiply its pressure times its volume and divide it by its temperature, and then you change that gas in some way, then if you put the gas into a new situation, let's say you change its volume, its pressure and its volume will change in the new situation such that the number that you get when you multiply P and V and divide by T in the former situation before the change takes place will be the same as when you multiply the pressure times the volume and divide by the temperature in the new situation. So this formula describes the pressure, the volume, and the temperature of a gas under changing conditions. So let's take a look at how we use this formula. So here's a question for you to try. And again, I'm going to pause here. We'll take a break after we answer this question. I'm going to pause here and let you have a crack at this question. So if a gas with a volume of 500 cubic centimeters and a pressure of 100,000 pascals, pressure is measured in pascals, is heated from 20 degrees centigrade to 30 degrees centigrade in a sealed container, what would the final pressure of this gas be? So think about, what is its initial volume? What is its initial temperature? What is its final volume? And what is its final pressure? And what is its final temperature? So think of it as a before and after statement. What is staying the same? What is changing? And which values do we know? And how can we use them in that previous equation? This is a little bit of a tricky one. So I'm going to pause for a little while here and let you have a crack at this question. So if a gas with a volume of 500 centimeters cubed and a pressure of 100,000 pascals, that's our starting volume and our starting pressure. It's then heated. It starts from 20 degrees C. it ends at 30 degrees C, and it's in a sealed container. Now, assume for a moment that by sealed container that the volume remains constant. If it's a sealed container and it's a kind of the sealed container has uniform dimensions and it doesn't change, the volume remains constant. So the final volume, here's a clue for you, the final volume will also be 500 centimeters cubed because the volume remains the same. It's in a sealed container. So what will the final pressure of the gas be? All right, so let's take a look at how we do this. So it's in a sealed container, so the volume is not changing. Volume 1 is equal to volume 2. The volume at the start is equal to the volume at the end, which is 500 centimeters cubed. Now, the starting temperature is 20 degrees centigrade. The final temperature is 30 degrees centigrade. So our starting volume and our final volume are 500 cubic centimeters. Our starting and ending temperatures are 293 Kelvin and 303 Kelvin. So how do we use this combined gas law to find the final temperature? Well, again, the final pressure rather. So we know the initial pressure, 100,000 pascals. We're trying to work out the final pressure. And again, to remind you, here is the combined gas law. So the starting pressure times the starting volume is divided by the starting temperature is going to be equal to the final pressure times the final volume divided by the final temperature. So we know P1, it's 100,000 pascals. We know V1 and V2, those are both 500. We know T1 and T2. So the only unknown here is P2. So we can substitute our values first to get this. And then we can rearrange this equation to find, to make P2 the subject. So we would multiply both sides by 303, then divide both sides by 500, and we get this. And then we evaluate this, the 500s cancel, so we get 100,000 times 303 divided by 293, and we get P2, when we evaluate this, is 103,412.9 pascals. So the final pressure would be 103,412.9 pascals. So well done to those of you who got that. It's a bit of a tricky problem, but well done. Okay guys, so it seems like we've come to the end of the first hour. Well done, and let's take a 5-minute break now. All right, so let's try another one of these examples of calculations using the combined gas law then. So, excuse me, despite all this hot weather, I feel like I'm coming down with a cold. Okay, so let's have a look. So if a gas with a volume of X centimeters cubed and a pressure of 150,000 pascals expands to a volume of 1,000 centimeters cubed and a new pressure of 75,000 pascals, and this happens at a constant temperature of constant room temperature, which again, let's just say that room temperature is 20 degrees centigrade in this case. What would be its initial volume? What is its starting volume? So we know the we're trying to find the volume X. At this volume, at this initial volume, it has a pressure of 150,000 pascals. So this is the initial pressure. And then it changes and expands. Its volume increases to a final volume of 1,000 centimeters cubed and a pressure of 75,000 pascals. So this is the final pressure. So what was the initial volume? Okay, so it seems like from the poll numbers, about 50% of you managed to answer this question correctly. The rest either didn't give a response or answered incorrectly. Some of you have typed your answers into the chat box. Okay, so some of them are correct, some of them not. Okay, so let's have a look at how we solve this question. So once again, what we need to do, and again, this is the kind of approach that I need all of you to try and get into the habit of using for exam questions as well. Have a look at the information you're being given. Try and, we know in this case which equation we're going to be using. We're going to be using the combined gas law, and then substitute the known values into the equation and then rearrange to find the solution, showing the steps of your working. So we know the initial pressure, 150,000. We know the initial temperature is 20 degrees centigrade, and it's constant temperature. And so the final temperature will also be 20 degrees centigrade, but we need to convert that into Kelvin. Because again, when you're dealing with these kinds of equations which are based upon the kinetic theory, we use the absolute temperature scale. Now, a change of 1 degree centigrade is the same as a change of 1 Kelvin, but in this, but you do need to use Kelvin as the standard units of temperature, unless you have a very good reason to do otherwise. So we need to convert 20 degrees into Kelvin, which is 293. We substitute our values into this side of the equation. 150,000 is V1. 150,000 pascals is P1, V1 is X. So we don't know what X is, we're trying to find out what X is. We know that the initial temperature and the final temperature is 293, so we substitute that into T1 and T2. We know the final pressure is 75,000, and we know the final volume is 1,000 centimeters cubed. So when we substitute those values in, we get this, and then the only unknown in the equation is V1. So in order to get V1 on its own on one side, to rearrange to make V1 the subject, we multiply both sides by 293 to remove this 293 on the left-hand side. We then divide both sides by 150,000 and we get this. Then we evaluate this and we find that the 293s cancel, and we get this, so we can just go ahead and evaluate. We get V1 is 500 cubic centimeters. Excellent. Okay, so we've talked about the behavior of gases. We've talked about the definitions of temperature and heat and internal energy. Now, we need to look at what happens to materials under the conditions where we're heating and cooling them. So heating is the process of adding heat energy to an object, so transferring energy in the form of heat from a higher temperature to a lower temperature. So what we're doing here in this example is we are transferring energy to the particles of this liquid, and as you can see, it is starting to boil. Now, the important thing here is that heating describes adding heat energy to an object at a greater rate than the heat energy is being lost from the object to the surroundings. So the temperature of the object will then rise above the temperature of its surroundings. Whereas cooling, on the other hand, this is the opposite process. It's the process of losing heat energy from an object at a greater rate than the rate at which the heat energy is entering the object. So the temperature in this case will fall below that of its surroundings. Now, two things can happen to materials when you heat or cool them. Either the temperature will rise, or when you reach a particular temperature for a particular substance, the temperature will not change despite the fact that you're heating and cooling. What will happen instead is that you get a change of physical state. So there are two different consequences to heating. Either you can get a change of physical state at unique temperatures like the melting or the boiling point, or the temperature of the object will simply rise. Similarly, there are two different things that can happen when you cool a substance down. Either its temperature will decrease, or when it reaches certain unique temperatures which are characteristic of that substance, it will change its physical state. So when you reach the condensation point, the gas will turn into a liquid at a constant temperature even though you're cooling it, and when you reach the freezing point, the liquid will turn into the solid even though you are cooling. You are removing heat energy, and so either the temperature will change or the substance will change state at a constant temperature. So let's look at the first of those situations where heating or cooling changes the temperature of an object. So for this we need to invoke the equation and the idea or the equation that concerns heating and cooling and changes of temperature. And for this we also need to invoke the idea of specific heat capacity. So the specific heat capacity of a substance describes the amount of heat energy transferred when a unit mass, 1 kilogram of the substance, changes its temperature by 1 degree centigrade. So a kind of an illustration of what we mean by specific heat capacity on a very basic level is, for example, let's say you take a pie and you put it in the oven. So when you take the pie from the oven, the filling stays hotter than the pastry does. So this is because the specific heat capacity of the substances in the filling is higher than the specific heat capacities of the substances in the pastry. So the specific heat capacity of a material is the heat energy needed to raise the temperature of 1 kilogram of the material. It is also specific to that material. So in other words, water has a unique specific heat capacity which is characteristic of water. Ethanol has a different specific heat capacity, which is characteristic of ethanol. So the units for specific heat capacity are joules per kilogram degrees centigrade. Now again, one of the advantages of memorizing your equations is that you never need to really memorize, or you can deduce the units of something if you forget them. So let me open up another document here, and let's use this to illustrate what I'm talking about here. Oh. Okay, so the equation for specific heat capacity should be familiar to you. This is one of those things that we mentioned briefly in the second webinar of this GCSE Physics series on energy. So under conditions of rising or falling temperatures. So the first situation that we're looking at here is when heating or cooling with change of temperature. So we're not talking about changes of physical state which happen at constant temperature. We're talking about what happens when we are raising or lowering the temperature of an object by allowing the temperature or by allowing heat energy to go into the object and heat energy to come out of the object. So let me clarify that rather confused statement that I just made. So again, when you heat something, you are adding energy to the particles of the object. Heat is the transfer of energy into internal energy of an object. So if heat energy is being transferred into an object, you are raising the internal energy because the particles of the object are absorbing energy and they're moving more rapidly. So there are two things that can happen. Either the temperature of the object can change when you add or take away heat from it, or the object can change state at a constant temperature. So heating and cooling with a change of temperature or change of physical state at constant temperature. So if the temperature of an object changes while you're adding or taking away heat energy from it, then this equation applies. The change in heat energy is equal to the mass times the specific heat capacity times the change in temperature. So change in temperature is delta meaning the change. This triangle here means the change in a quantity. Theta is a symbol which is often used in this equation to describe the temperature. So the change in heat energy is going to be measured in joules. The mass, again, standard units is kilograms. The change in temperature is going to be measured in Kelvin. Now, in the case of this equation, because you're measuring a change in temperature, an increment of 1 Kelvin, a change in temperature of 1 Kelvin is equivalent to a change of temperature of 1 degree centigrade. So this can be in degrees Kelvin or it can be in degrees centigrade. Either one of these would be applicable to in this equation. So if this is the equation that describes how the change in heat energy is related to the change in temperature of a substance, then the specific heat capacity of a substance, if we look at how we define its units, so this is specific heat capacity, to determine the units, let's say you've forgotten the units of specific heat capacity and you want to work it out, you can just rearrange this equation to make C the subject and then look at what the units are telling you. So if we want to make C the subject of this equation, we need to divide both sides by m times delta T, because the term C is being multiplied by m times delta T here. So to undo that, you need to do the opposite. You need to divide both sides by m times delta T. So when you do that, you get C equals delta E divided by m delta theta. Sorry, I'm using the term delta T here, which delta theta is the change in temperature. So let's have a look at the units now. So it's joules. Oh, for some reason I've lost the ability to write. So joules, this is the units for the change in heat energy. Again, mass is in kilograms, and delta theta, the change in temperature, let's just say is in degrees centigrade. And so the units of specific heat capacity are going to be joules divided by kilograms times degrees centigrade. So this specific heat capacity, the units are going to be joules per kilogram degrees centigrade. So if we look at the units now, the units tell us the definition of specific heat capacity. It's the amount of heat energy change that occurs per kilogram of mass for every 1 degree centigrade rise or fall of temperature of that 1 kilogram of mass. So that's what specific heat capacity is. Let's take a quick look at a little bit more about it. So this is the equation that we've just seen here. So energy transferred, the heat energy transferred to or from a substance, is equal to the mass of substance in kilograms times the specific heat capacity in joules per kilogram degree centigrade times the temperature change in degree centigrade if you're using these units of specific heat capacity. So specific heat capacity is a property of a material. It's unique to each particular substance, each element or compound, for example. It has that uniqueness because every material is made up of unique types of particles with unique types and strengths of bonding between those particles. So let's take a look at a calculation then. So here's a calculation for you to try. Calculate the heat energy transferred when we take a large bathtub full of water, and let's just assume that the amount of water in the bathtub has a mass of 900 kilograms. Now let's take that bathtub of water, and let's say the water starts at 40 degrees centigrade and then cools down to 20 degrees centigrade. What is the heat energy which has been transferred during that cooling process from that 900 kilograms of water? And for this, you're going to need the specific heat capacity of water, which is 4,200 joules per kilogram degree centigrade. Here's how you calculate it. So the heat energy transferred is equal to the mass in kilograms, which we have, times the specific heat capacity in standard units, which we have, times the change in temperature. So the change in temperature is 40 minus 20. So that's the difference in the starting and the ending temperature. It's 20 degrees centigrade. So we substitute those values, we evaluate, and we get 75,600,000 joules. Now, this is 75,600 kilojoules of energy. Now, this gives you a sense of just how much energy, how much thermal energy water can store. In fact, this is about enough energy to run the average PC or average computer for about 9 days. So this is part of the reason why having a shower instead of having a bath will save a lot of energy, because it takes a lot of energy to raise the temperature of a unit mass of water, even by a relatively small temperature change. Good, well done. So again, just remember the rate at which a substance transfers heat energy can be calculated using that formula, but you would need to rearrange this equation in order to calculate the mass or the specific heat capacity or the temperature change. So now, speaking of changes in temperature, before we get into changes of state, changes of physical state, there are 3 main ways in which heat energy can be transferred from a hotter object to a colder object, or from a hotter place to a colder place. These are conduction, convection, and heat radiation, thermal radiation. So heat is effectively transferred, again, remember, from a higher temperature to a warmer temperature. This is, in essence, this gives rise to the theoretical definition of temperature. It is the quality of materials which will determine the direction of heat energy transfer. So let's start with conduction then. So this is a simple experiment which you may have seen done. We have a copper rod balanced on a tripod. It's going to be heated at one end, and we have a drawing pin stuck with a bit of wax at the other end. So this is copper. Copper, like most metals, is a good conductor of heat. So we start the heating, and the thermal energy which is being added to the particles at this end will be transferred by conduction to the point where the thermal energy will increase at this end, which will be enough to melt the wax to cause the drawing pin to eventually fall off. Now, the way that this works in terms of the actual motions and the arrangements and of the particles is like this. So if we imagine that this end is being heated, the internal energy at this end is increasing because heat energy is being transferred to increase the kinetic energies of the particles at this end. But the particles collide with the ones near them to transfer that thermal energy. So as they transfer it, these particles start to move faster, which makes these move faster, which makes these move faster, so that the thermal energy is being transferred along the material. So the increase in kinetic energy at the hot end of the object is being passed on to adjacent particles through collisions between particles, and this is what transfers the heat energy along by conduction. So this is the mechanism for conduction. Now, I mentioned that metals are particularly good conductors of heat energy. Now, part of the reason for that is not just because of the collisions of the particles, but because in metallic structures, the outermost electrons of these metal atoms are shared between the metal atoms and are able to move. We say that those electrons are delocalized. So when you heat a metal at one end, it's not just the collisions between the positively charged metal ions which transfer the thermal energy along. The delocalized electrons will also transfer the energy along. And it's the same reason why metals are particularly good at conducting not just heat energy, but also electrical energy as well. So metals are much better thermal conductors than non-metals, and therefore metals conduct heat more effectively than non-metals. So in metals, the transfer of heat occurs very quickly, but in non-metals it tends to be slower. Many non-metallic substances are poor conductors of heat and are therefore useful as insulators. So what you're seeing here is the kind of fiberglass wool which is used in loft insulation, and the non-metallic compounds, these plastics and so on, which are used in insulated clothing. So the other method by which heat can be transferred, in particular in liquids and in gases, is by convection. So this experiment, which you may have seen demonstrated, illustrates how convection works. So convection can only occur in liquids and gases because it's only in liquids and gases where the particles can move translationally in random directions. It can't take place in solids because solids, the particles in a solid are unable to move other than to move vibrationally. So we have here a crystal of potassium manganate 7, which is a kind of purple crystal, which dissolves very readily, sitting in a liquid here. If we then heat this corner of the beaker, the crystal will slowly dissolve, and the purple solution that's formed will increase its thermal energy here, so the particles will move further apart from each other because of their increased kinetic energy. This causes them to become less dense, and therefore the warm solution will rise because in comparison to the surrounding colder solution, it is less dense. As it rises, it is giving up some of its thermal energy to the colder particles around it by collisions, and so eventually it will become more dense and then will start to fall, and this sets up a convection current which causes the fluid to flow around the beaker in this manner. So, as the warm water reaches the top, it starts to cool, becomes more dense, sinks to the bottom, only to be heated again and to rise again. So this circulating movement of particles is called a convection current, and the same thing will happen in gases as well. This is a similar principle by which radiator boards will heat up a whole room. Okay, so domestic radiators actually transfer most of their heat by convection, not by radiation. So it's actually a misnomer to call it a radiator. It's actually more of a convection heater. So what we have here is a domestic radiator board. It's giving off heat energy. That heat energy is being absorbed by the air molecules which collide with the surface of the radiator and also absorb infrared radiation from the radiator. So this causes those particles to move more rapidly in the gas state. This causes them to the particles to move further apart. That means that region of gas is becoming less dense than the regions of gas around it. This causes them to rise in relation to the colder regions of gas around them. As they move upwards, they displace the cooler air near the ceiling, and in doing that, the cooler air then falls to take the place of the hot air near the radiator. And so in this way, we get a convection current started, which then when the cold air returns to the radiator, it gets heated again. But eventually the whole room will the air in the room will rise in its average temperature because the radiator board is transferring thermal energy to the particles in the room. The energy is being distributed around the room by this convection current. So the third form of heat energy transfer is by infrared radiation. So what you're seeing here is a FLIR camera. This is an infrared imaging camera which has been pointed at a laptop and a screen. And as you can see here, there are certain parts of the image which are brighter than the other surrounding parts of the image. So the brightness indicates a measure of the temperature of the objects that you're pointing this camera at. So thermal radiation is the process by which heat is transferred as infrared waves. Infrared waves are part of the electromagnetic spectrum, and they have longer wavelengths than visible light. So the electromagnetic spectrum is something that we're going to be covering in a later webinar in this series on the topic of waves in physics, but for the purposes of this topic, let's just take a look at it briefly here. So there are 7 forms of electromagnetic wave in the electromagnetic spectrum, and the spectrum extends from the long wavelength low frequency radio waves to the short wavelength high frequency gamma waves. Now the frequency is a measure of the amount of energy that these waves carry. So the longer wavelengths correspond to the longer or the lower frequencies, and so at the long wavelength end you've got radio waves, at the short wavelength high frequency end you've got gamma rays. So as you can see here, the infrared is the region of the electromagnetic spectrum. These are electromagnetic waves which have wavelengths longer than the red of visible light, but because wavelength is inversely proportional to frequency, these waves have a lower frequency than red visible light, and this is what infrared actually refers to. Infra means below or underneath, and so these are electromagnetic waves which have a lower frequency than the red of visible light, hence infrared, below the red. Similarly, ultraviolet, ultra means above or beyond, and so the ultraviolet waves have a higher frequency than the visible violet waves. So these are beyond the violet or ultraviolet. But these are all the same phenomenon. These are all just waves of electric and magnetic fields which transfer energy through space. The only way that they differ is in their frequencies and their wavelengths, but they are all the same kind of phenomenon. So infrared radiation typically has a frequency of 10 to the power 11 to 10 to the power 14 hertz, and a wavelength, this should say in meters, apologies for that, wavelength in meters of about 10 to the power minus 3 to 10 to the power minus 6. So this is the range of frequencies where you find the infrared radiation in the electromagnetic spectrum. This is the range of wavelengths where you find it. So it occurs just beyond the visible spectrum. It's also sometimes called heat radiation or radiant heat. So infrared thermal imaging cameras like the FLIR camera that you saw before, which is basically the same technology which police cameras use as well on police helicopters, like this FLIR camera here that you're seeing here. So they convert heat radiation into electrical signals which are then displayed on a screen as visual information. So this can work in the dark, and sometimes it's called night vision equipment for this reason. So infrared cameras are used in various different contexts. They're used by engineers and architects to find out which parts of buildings are losing heat most rapidly for better insulation. They can be used to find people trapped in collapsed buildings during earthquakes. They can also be used by police to track runaway offenders at nighttime in helicopters. So unlike conduction and convection, infrared radiation does not require the motions of particles. It can be transferred through a vacuum, and in fact it is. We get a lot of infrared radiation from the sun, and in order to get to the Earth it has to go through the vacuum between the sun and the Earth, and obviously there are no particles there. So infrared radiation is a form of heat transfer which does not require particles. Now, all electromagnetic waves travel in straight lines, and they all travel at the speed of light in a vacuum. And so infrared radiation, being an electromagnetic wave, also travels at the speed of light in a vacuum in a straight line. So objects which are warmer than their surroundings will emit infrared waves at a more rapid rate than they absorb them, whereas cold objects, objects which are colder than their surroundings, will absorb infrared radiation at a higher rate than they emit it. So this kind of speaks to a common misconception that a lot of students have, in the sense that when they describe emission or absorption from hot or cold objects, they will often say that a hot object emits infrared radiation and a cold object absorbs infrared radiation, but they often miss out the fact that actually both objects will emit and absorb radiation, infrared radiation. The difference is that a hot object will give off infrared at a higher rate that it absorbs it. It is still absorbing it from the surroundings, but it's absorbing it more slowly than it's giving it off. And the opposite is true of a cold object. So if the temperature of an object remains constant, then it must be absorbing and emitting heat at the same rate. So this is another common misconception, the idea that if an object is at the same temperature as its surrounding, it is not absorbing and it is not emitting. That's not strictly speaking the case. It is absorbing heat, it is emitting heat, but the two processes are happening at the same rate, and so there is no net absorption or net emission. So when you sit by the fire, you can immediately feel the warmth on your body, and this is because the heat energy is reaching you from the fire by infrared radiation. But eventually you will reach a temperature at which you will reach a point where your temperature will not rise, and the reason for that is that your body is actually radiating heat at the same rate that it's absorbing it. That temperature may be relatively uncomfortable, and at that point you might move away from the fire. So different surfaces will absorb and emit heat at different rates, and this experiment here illustrates this principle. So here we have a Bunsen flame. Here we have two surfaces, both of which are the objects are made of metal, but the surfaces are coated with different types of paint. So the surface of this object is coated with a matte white paint. The surface of this object is coated with a matte black paint. On the side of these two objects opposite from the Bunsen, we have a blob of wax to which we've stuck a ball bearing. So if we now start this experiment and see what happens, we'll see that the object with the matte black coated metal will have its ball bearing drop first. And the reason is that a matte black surface will absorb heat radiation more rapidly than a matte white coated surface, and therefore the wax on this side of this object will melt more rapidly than the wax on this side of the object, and this will cause this ball bearing to fall first. So let's take a look at another example that shows the difference, this time in emission, in how different types of surfaces give off heat radiation. So here we have a container filled with hot water, and it has four sides. Now this time there are two different types of black paint. There's shiny black paint on this side, on the outside of this surface, and there's matte black paint on the outside of this surface. On this side we have matte white paint, on this side we have shiny white paint. So I'm going to pause here, and I'm going to let you guys decide which of these is going to absorb heat energy most rapidly. So here we have thermometers which represent the temperature of these sides of, or rather which of these sides will emit the heat energy from the hot water into the surroundings at the highest rate. So these thermometers are positioned opposite each one of these four sides. Which of these thermometers opposite which of these sides will rise in temperature at the highest rate? All right, so now this is interesting because this is another one of those things which we find a lot of misconceptions. Now think about this. The surface of a material will, if it absorbs energy well, now in the previous example we were just dealing with matte white and matte black, and we saw that matte black absorbs heat energy better than matte white surfaces. Now the surface, heat energy is just heat energy, so the direction that it goes in is going to be the rate at which it passes through a surface in either direction is going to be the same if that surface remains the same and the temperature difference remains the same. So in fact, if we start this experiment, we'll see that actually the matte black surface absorbs the heat energy fastest, closely followed by the shiny black surface, followed by the matte white, followed by the shiny white. And so matte surfaces in general, whether you're talking about black or white, matte surfaces absorb and emit heat better than shiny surfaces. Black surfaces will absorb and emit heat more rapidly than shiny surfaces. Now, shiny kind of gives it away a little bit because shiny implies reflectivity. Shiny surfaces tend to reflect radiation better, which means that they're less likely to be able to emit and absorb radiation particularly well. So, in terms of the order here, matte black is going to be the best, followed by shiny black, followed by matte white, followed by shiny white. All right. So just remember, the matte is always better at absorbing and emitting than shiny. Black is always better at absorbing and emitting than white. Right, so speaking of reflection of radiation, so in addition to the absorption and emission of infrared radiation, reflection also plays an important role in the transfer of energy by radiation. So radiation can be reflected by surfaces just the same way, or infrared radiation can be reflected by surfaces just the same way that light can, because again, infrared radiation is an electromagnetic wave like light. And so a substance which is a good reflector of heat tends to be a poor absorber of heat. So as we saw, a light shiny surface is a good reflector, or rather is a poor absorber, but that means it's going to be a good reflector. A substance which is a poor reflector of heat is going to be a good absorber of heat. So as we saw in the previous example, a dark matte surface is a poor absorber and a poor emitter. Absorption and emission are affected in the same way by the same types of surface. But reflection is something different. If something is a good emitter, it's going to be a poor reflector. If it's a good absorber, it's going to be a poor reflector. So a substance which is a poor reflector of heat is a good absorber of heat, and so a dark matte surface is a poor reflector of infrared radiation. So speaking of thermal imaging cameras, so this thermograph was taken with a FLIR camera. This shows the different temperatures of parts of this person's body here. The red areas are warmer than the blue areas, and as we can see here, the face is the hottest part of the image here. So there's a heat source also on the right hand side, which shows in the red areas of the jumper. So perhaps this person is standing in sunlight and the sunlight is falling on their left, or which is our right. On that side. So doctors can also use similar equipment to assess the state of the human body, because sometimes internal disease conditions will manifest themselves as changes in the thermal properties of various parts of the body, which can be detected by thermal imaging cameras. So again, cooler areas will show up in shades of blue, and this may inform a doctor of a problem in that part of the body. Cancer tissues, for example, are hotter than normal body tissues, and this can be detected in this way as well. Now, in the previous topic, we were talking about thermal energy, but in this topic, depending on your exam board, either in the energy topic or in the kinetic theory topic, you need to know a little bit about insulation. So we can measure, using thermal imaging, the heat energy coming from a building to find out which parts of the building are losing energy by infrared radiation at the most rapid rate. And as we said before, there are other uses of these FLIR cameras, these thermal imaging cameras, including to detect the survivors of natural disasters who might be buried under the rubble. So here is a photograph of a house taken with a thermal imaging camera. We can see here quite clearly that around this door frame and also some of the windows, these are the regions where a lot of heat energy is being lost from the house, and also the underside of the gutters here around the edges of the roofs in these sections here. So firefighters can also use thermal imaging as a source of key information as well. And thermal imaging is often used by satellites to study the Earth's climate and the effects of anthropogenic climate change. So this thermal image shows the temperature of the oceans. As we can see, fairly predictably, the equator has the highest average temperature around the middle. There are some other uses of infrared radiation. So we see here television, video, DVD and CD remote control handsets. These all use infrared radiation for signaling. Now the waves don't actually penetrate very far, so these devices are only really useful over short distances. Now another application is infrared heat lamps, which can be used to either incubate organisms like young chicks in farms, but they can also be used for heat treatment of injuries as well. So the size of an object will also affect the rate of heat energy transfer as well. So let's imagine that we have two objects here. So imagine we have two beakers. Both beakers contain water at 80 degrees centigrade at the start of the experiment, but this beaker contains 500 milliliters of water, whereas this beaker contains only 100 milliliters of water. So make a prediction. I'll pause here for a sec. Make a prediction. Which of these will cool the most rapidly? Okay, yeah, so it seems like almost everybody, with the exception of one or two people who didn't answer the question for whatever reason. Yeah, so let's start this experiment and see what happens. So we can see here that it's the smaller volume of water which is going to cool the most rapidly. Now the reason for this is, again, they both started at the same temperature, but this object has more internal energy because it has more particles, and so those particles contain more thermal energy, more internal energy at this temperature than this object does at the same temperature. The bigger the object, the more the internal energy is, and therefore the lower the rate at which that object will lose energy to its surroundings by, in this case, radiation and conduction and convection within the object. Well done. So let's try another thing here. So in this case, we have two containers. They have the same volume of water. Both have 500 milliliters of water. They both start at the same temperature. In this case, it's the shape of the containers which is the variable here. So make a prediction. Which of these two containers will have the in which of these two containers will the water cool the most rapidly? Great. Okay, yes. So again, almost unanimous. Yes, correct. So if we have a look at the experiment, we see again the shallower container with the larger surface area is going to cool more rapidly than the same volume of water in a container which has a lower surface area to volume ratio. Now that's the reason for this. It's because of the surface area to volume ratio. The volume is the same, but this container has a greater surface area through which heat can be lost to the surroundings. Great, well done. So here's another one. The temperature difference. So this time we have two of the same volume of water, same shape of container. They start at the same temperature. So which of these two is going to cool most rapidly? Should need less time. This one's a little bit more obvious. Yes, well done. Yeah, so it's obviously going to be the one in the fridge. But the reason for that is, again, goes back to the difference in temperature between this object and its surroundings here versus this object and its surroundings at room temperature. The temperature difference is going to be less between this object and its surroundings and this object and its surroundings. So when the temperature difference between two objects is bigger, the rate of heat transfer is higher. And again, this goes back to the idea that temperature is a measure of the average kinetic energies of the particles. So the particles out here have a very low kinetic energy, and so they absorb the higher kinetic energies of these particles by conduction and radiation more rapidly. Now, it also goes to the actual theoretical definition of temperature. Temperature is what determines the difference in temperature between two objects, is what determines the direction and the rate of heat flow. The bigger the difference, the faster the rate of heat flow from the hotter object to the colder object or its surroundings. Excellent. So that takes us to the end of the topic teaching. Let's finish off with just one quick example of the thermos flask to round off what we're talking about. So the thermos flask is a device which is designed to minimize the rate of heat loss, or the rate of minimize the rate of change of temperature, because it can also keep things cool, by minimizing the rate of transfer of heat by conduction, convection, and radiation. So it can keep hot drinks and soups at a hot temperature for longer. It can also keep cold drinks at a cooler temperature for longer on hot days. Now, it is delicate. It's a delicate device, and it needs to be protected from hard knocks, but it's specifically designed to minimize the rate of heat transfer from inside the substance inside the thermos flask to the surroundings if the substance is hotter than the surroundings, or it's designed to minimize the rate at which heat enters the cool liquid inside the flask from the hotter surroundings. Now, this is to do with its design. So what we have here is a plastic cup over the top. Plastic is a good insulator. We have here a plastic cap, which is also a good insulator. We have a double-walled container. The two walls are made of silvered glass, and they have a vacuum in between them. And the vacuum contains no particles, so that prevents the transfer of heat by conduction or by convection. The walls are silvered, and so this prevents or minimizes the radiation, because again, silvered surfaces are poor emitters. Reflective surfaces are poor emitters of radiation. We have a plastic outer casing, which again, it minimizes heat transfer by conduction because it's a good thermal insulator. And we have a sponge pad holding the very delicate double-walled glass flask in place, and the sponge itself contains numerous air pockets, and air is also a poor conductor because the particles in a gas are very widely spaced apart. So here we can have a hot or a cold liquid, and we have inner silvered walls. So this vacuum flask is it's actually made by kind of a process similar to glass blowing, and so it needs to be sealed while the glass of those walls is still liquid. And so this little area here represents the vacuum seal. We also have a sponge or spring cushion on the bottom here, which is, these sponge pads and cushions are partly for insulation to prevent conduction from the walls of the double-walled flask to the outside, but it's also there to protect from vibration in case you drop the flask, because again, the internal double-walled container, which is made of glass, is quite delicate. So the top insulating cap, made of plastic to prevent heat loss by conduction. We have the double-walled container separated by vacuum to prevent conduction by loss of heat by conduction and convection. We have the foam liners, the foam pads, to prevent heat loss by conduction. So basically, every aspect of this is designed to minimize the heat energy transfer by those three methods. The inside surfaces of the thermos flask are silvered in color, and this provides a reflective surface which prevents heat loss by radiation as well. Okay guys, so I see that we've come to the end of the second 1 hour segment. So at this point, I'm going to again give you a 5-minute break. Yeah, so it seems like about 65-70% of you also voted for Q&A. That's fine. So again, just be aware that I will be posting the mark scheme for these exam questions, as always, to the private webinar resources page, along with all the other resources within the next 48 hours or so. So let's have a look at the questions that have been asked across the 5 Zoom webinar rooms and see which ones have received the most upvotes here. Okay. Right, so a lot of students have asked a question concerning sublimation. So let's have a look at, go back to the bit that concerns that. So yes, there is a change of state called sublimation, which involves the change directly from the solid state to the gas state. Now, this only applies to certain types of substances. Now, one of the substances that you may have come across that does sublime, so sublimation is when a solid will change its physical state directly into a gas. And also, when a gas is cooled to its sublimation point, it will also turn directly back into a solid with no liquid state in between. So yes, sublimation is a type of change of physical state, which we didn't mention earlier on, and that does happen. Now, one of the substances for which that happens is carbon dioxide. Carbon dioxide, you can get solid pellets of carbon dioxide, which is commonly referred to as dry ice. It's not water ice. It is solid carbon dioxide. Now, when that carbon dioxide reaches a particular or absorbs thermal energy, it will turn directly from the solid to a gas, and so that is sublimation. So I hope that answers your question. The next question concerns changes of physical state and specific latent heat. So that seems to be by far and away the next question that's been asked, or the question that's received the next highest number of votes. So let's quickly run through the change of physical state from or rather the equation that determines the change, the heat energy change during a change of physical state. So I mentioned that heating and cooling, when a change of temperature takes place, the particles of the substance are absorbing the heat energy, and the internal energy of that substance is increasing, and therefore the motions of the particles are becoming more rapid, and so the temperature rises. Similarly, if heat energy is emitted from that object faster than it's absorbed, then the internal energy of the object is decreasing, and therefore its internal energies or rather the motions of its particles become less rapid, and its temperature will fall. But at a temperature which is characteristic of the substance, you get a change of physical phase. So the equation that applies then is a different equation to the one that we've just seen here. It's this one. So for a change of physical state, all changes of physical state other than evaporation, which happens at any temperature, happen at a constant temperature. So there is no delta E term in this equation. It's simply the energy, heat energy change that takes place is equal to the mass multiplied by a value which is called the specific latent heat. Specific latent heat. So this is mass in kilograms. Again, standard units of mass, kilograms. This is the heat energy change. So what we're saying here is that, and this concerns heating and cooling curves. So what we're saying here is, if we were to heat or cool a particular material, so let's just draw a general heating or cooling curve here. So I'm going to draw a couple of axes here. So here are two axes which represent the temperature on the vertical axis. So this is the temperature, so this is the temperature, and let's just assume to start with we start at some starting temperature. So here is our starting temperature, and we are heating starting from this time. So on this axis we have time of heating. So we're doing an experiment where we start with a substance and we start to heat that substance. Now let's assume, for the sake of argument, that we start with that substance in the solid state. So it's at the solid state at a particular temperature that we start from. Now, as we heat that substance, it will change its temperature, and the temperature will rise. Let me just do that again, because that's very messy. So the temperature will rise as we start to heat that substance. So we are starting to heat at this point. So this is time equals 0. At this point, we start our heating. So we're supplying energy. We're supplying heat energy to the particles of that object. The particles are moving more rapidly, and therefore the temperature is rising, because temperature is a measure of the average kinetic energies of the particles. And so during this portion of our experiment, from here to here, the equation that applies to what's happening is this one. We're providing heat energy, the object is absorbing heat energy, its particles are moving more rapidly, and so its temperature will rise. However, we will eventually reach a temperature which is called the melting point. So again, we're starting with a solid substance, but we reach the melting point temperature. Now remember, we're continuing to heat. So let's say this is the time at which we reach the melting point temperature in our experiment, but we're continuing to heat beyond this time. What we would observe is that even though we're continuing to heat, at the melting point, the object will melt, but it will melt. It will melt at a constant temperature. So we continue to heat, but the object stays at the same temperature during that time period while it's melting. So during this period of time, here, not a very good line, but you get the idea. So during this period of time, between here and here, this is where we have melting taking place. Oh. Let me write a bit more clearly here. Melting. So once we get to this point in our experiment, remember we've been continuously heating. Once we reach this point, we have turned the solid into a liquid. So here we started with a solid. This is where melting is taking place. The solid is changing to a liquid. But at this point, from this time onwards, we have a liquid. Now, because we're continuing to heat, what will then happen is that the temperature of the liquid, again, will rise. So we are supplying heat energy to the liquid. The temperature continues to rise until eventually we hit another temperature. Another temperature which is characteristic of that substance, which is called the boiling point temperature. So here we have the boiling point temperature. So once we reach the boiling point temperature, again, what will happen is we have something else which is going to occur here. We continue to heat, but the temperature does not rise because during this portion of time, during this portion of our experiment, the substance is boiling to become a gas. So at this point, let me do this. So between here and here, so during this duration, we have boiling taking place, and boiling happens at a constant temperature called the boiling point. So now at the end of this period we have a gas, and then if we continue to heat that gas, it will simply continue to rise in temperature. So this is what sometimes is called a heating curve. It's not really a curve, but it's called a heating curve. So we start with a solid. We start heating at this point. We continuously heat all the way through this experiment. Now, during these portions of the experiment, where you have a solid or a liquid or a gas, providing heat energy to the solid, the liquid, or the gas is simply transferring heat energy. The particles absorb the heat energy. The internal energy of that object is increasing, so the particle motions are becoming more rapid. The average temperature or the average kinetic energies of the particles are increasing, and so we say that the temperature increases during these portions. So it's fairly easy to see what's happening to the heat energy that we're supplying during these parts of the experiment. The heat energy that we're providing to the object is being transferred into the internal energy store of the object. The particles of the object are moving more rapidly. However, during melting and during boiling, even though we're heating continuously, the temperature isn't increasing. So what's happening to the heat energy then? Well, what's happening is the heat energy is not just disappearing. It's being used not to increase the rate of motion of the particles. In other words, it's not being used to increase the average kinetic energies of the particles. It's being used to overcome the forces between those particles so that we can go from being a solid to a liquid or from being a liquid to a gas. And so this is where the word latent comes from. The word latent means hidden. So latent heat is the heat which doesn't seem to be changing the temperature of the object during changes of state. It is, in fact, not changing the average kinetic energies of the particles. It's not changing the temperature. The energy that we're supplying during melting is being used to overcome the forces of attraction between the particles in the solid so that the particles can move past each other and enter the liquid phase. And so specific latent heat is the amount of heat energy which is used to either melt or boil 1 kilogram of that substance at a constant temperature. But also we can use the same logic to describe cooling. Now I'm not going to draw a cooling curve, but imagine instead we started at this temperature and we cooled continuously. Let's say the time axis went from here at time equals 0 to this side. So in fact, let's draw that in a different color. And again, I'll make these whiteboard notes available to all of you on the private resources page as well. So let's imagine that we have 2 axes here. So 2 experiments. So let me draw this one. All right, so this axis here represents temperature for this experiment, but in this experiment, the time axis goes in the opposite direction. So this is our time axis for the second experiment, where instead of starting with a solid, we start with a gas. So this is time of cooling. So here, time equals 0, we start cooling. So we're starting with a gas. We cool the gas down. We're taking heat energy away from the object. So the gas molecules are losing their average kinetic energies. Their kinetic energies are decreasing. Therefore, the temperature is decreasing. Then we hit the same temperature as the boiling point, but this temperature, when we're cooling, is called the condensation point, because that's what's happening. Condensation point. So during this portion of this cooling curve, this is when condensation is happening, because the gas that we're starting with is changing to form a liquid, but it's changing at a constant temperature despite the fact that we're removing heat energy from the gas. So again, in this case, heat energy is being lost from the gas into the surroundings. So once we've condensed all of the gas to form a liquid, and we continue to cool in this direction as time goes on, we have a liquid now because all of the gas is condensed. The liquid's temperature simply falls until we reach the same temperature as the melting point, but because we're cooling, it's not called the melting point, it's called the freezing point. So once we reach this temperature, we continue to cool, we continue to remove heat energy from the liquid, but what's happening is the temperature is not changing. It's remaining at this temperature during this period of time here. So this corresponds to the period of time in our cooling experiment where the liquid is freezing to become a solid. So once all of the liquid has become solid, the solid, we continue to cool it, and its temperature simply decreases. So we can see here that all of these changes of state, melting, boiling, freezing, condensing, they all happen at a constant temperature, despite the fact that there is a heat energy change involved. Because again, when we were heating, we continued to heat to get the thing to boil, but its temperature didn't change, and so the heat is hidden. So specific latent heat refers only to changes of state. So if we had to give a definition for specific latent heat, we could give it something like this. So specific latent heat is defined as the heat energy change that is associated with the change of physical state of 1 kilogram of a substance at a constant temperature. So it's the heat energy change that's associated with the change of physical state, not increasing or decreasing the temperature of 1 kilogram of a substance like we talked about in this situation, where heating changes the temperature of an object. In this equation, there is no term for change of temperature because there is no change of temperature happening during changes of physical state. So if we wanted units to accompany our definition of specific latent heat, we have the units for heat energy change, it's simply joules. We have the units of mass, which is kilograms. If we rearrange this equation to make L the subject, we get specific latent heat, L, equals the energy change per unit mass, or the energy per unit mass, which is energy divided by mass. So the units for specific latent heat are going to be joules per kilogram. The amount of heat energy in joules which is required to melt or boil something, or the amount of heat energy in joules which is given off when you condense or freeze something. So this is what specific latent heat means, and it's hidden because in this case, when you're changing the temperature of something, you're adding heat energy or taking away heat energy, and what that's doing is it's being transferred to or from the kinetic energy store of the particles of an object. In this case, it's being added or taken away not from the kinetic energy store, but from the potential energy store. So the fundamental difference between these two processes is that they both relate to internal temperature. Temperature is, internal energy. Internal energy is the sum of all of the kinetic and potential energies of all of the particles which make up an object. So remember, in the energy topic, we said the energy of a system is always the sum of the potential plus the kinetic energy. Now this applies to external energy. So for example, in this situation, the total energy of the system at this point is equal to the total energy of the system at this point. At this point, it's all potential energy and no kinetic energy. But then as it rolls down the hill, the energy of the system is transferred from potential to kinetic, but the total amount is the same. This is external energy because we're talking about the macroscopic scale, a boulder, something the size of a boulder. But this also applies to internal energy of a system or an object as well. The internal energy of an object, like a boulder, is when you add together all of the kinetic and potential energies of the particles that make up the object. So, in the case where you're changing the temperature of something by heating or cooling it, in this case, what's happening is the energy change, delta energy change, is equal to the energy change of the kinetic energies of the particles. So this is the heat energy change. But that change is not changing the potential energies of the particles, it's changing the average kinetic energies of the particles. Changes. So this equation here applies to this situation where the temperature of an object is changing. But when something is changing its physical state at a constant temperature, what this means is you are supplying heat energy to an object to melt it or to boil it. You are taking away heat energy from an object when you condense or freeze it. The difference here is the heat energy change that takes place is not changing the average kinetic energies of the particles. It's not changing the temperature. It's changing the bonding between those particles. And remember from that topic on energy, potential energy is the energy associated with the position and the arrangements of things. And so what's changing here is not K, but the potential, delta U. So U is changing while the kinetic energy is the average kinetic energies of the particles of the object is remaining constant. So here, the heat energy change is associated with the change in potential energy of the particles, i.e. bonding. So I hope that answers your question, and that takes care of specific latent heat and latent heat as a concept in general. All right, so let's have a look and see if there are any other questions being asked here. The third highest, or the question that received the third highest mark in various forms across all 5 of the Zoom rooms is to do with those surfaces. Now, you've all asked slightly different questions about surfaces. Some of you have asked, why do matte surfaces, why are matte surfaces better at absorption and emission than reflective surfaces? Well, again, it goes to the idea of reflectivity. If a surface is reflective, it means that energy, electromagnetic waves like light and also heat and things like that, will bounce off it rather than be absorbed by that surface. A matte surface is rougher, generally speaking, than a smooth reflective surface. The reason why reflective surfaces reflect electromagnetic waves like light is because the waves literally bounce off those surfaces and bounce off roughly parallel to each other, whereas matte surfaces are rougher and the waves don't bounce off them quite as parallel to each other. So you can't see your face in a matte surface the same way you can in a reflective surface. Now, the reason why they absorb and emit, or why black surfaces absorb or emit energy, thermal energy better than white surfaces, it has to do with the idea of black body radiation and waves. Now, seeing as I don't want to kind of go beyond this topic, that is something that we're going to be covering in the waves topic. But essentially, it's to do with electrons and energy levels and the nature of the actual atoms and molecules that make up those surfaces being different, and therefore absorbing and emitting energy differently. Typically, when infrared and also other electromagnetic waves are absorbed and emitted, it is done usually by electrons in atoms and molecules. And so if those electrons are arranged differently in atoms and molecules and have different energy level differences between their atomic and molecular orbitals, they will absorb and emit infrared and other electromagnetic radiation to differing extents and at different wavelengths and frequencies. So without going too much into that other topic and too much beyond the spec, that is the answer to that question. Okay, guys, so it seems like we've come to the end of the Q&A segment. I hope that was useful to you. As always, if you have any further questions, you can continue to correspond with me and send me questions either privately or through the live chat on the private resources page for this webinar on my website. Again, I will be posting the mark schemes for the exam questions, the slides that you've been seeing, the whiteboard notes, some simulations as well. I will embed those on that page so that you can have a play with those as well. And as always, any questions, please do send in those forms, and I'll be happy to respond to those all the way up to your final exams at the end of June. But until then, that's it for today's webinar. Again, I hope that was useful to you, and I will see you in the next one. Take care.